when a very large star, something bigger than 8 solar masses, collapses, when the core collapses, then what happens is you get something else. You don't get a white dwarf because you're squeezing everything down to just this tiny little speck. And so that's our next topic here, what we call this, the neutron stars. We introduced the term last time, but we'll explain more. 1932, physicists were studying atoms, physicists and chemists, and they realized that an odd thing was going on. And that is, for example, that you had atoms that seemed to weigh too much. For example, helium had twice the number of protons and twice the charge in the nucleus as hydrogen, but it clearly had 4 times the mass. And so something else was going on here. But some helium was weird. Some helium had 3 times the mass. It was 3 and 4 times the mass. And then, for example, carbon was discovered that it had 6 electrons, and so 6 protons, but it generally weighs 12 times what hydrogen does. And then some carbon weighed 13, and then some carbon that was radioactive weighed 14 times as much as hydrogen. And so this led James Chadwick to come up with the idea that there's another particle there that we're not actually seeing. And we weren't seeing it because we were looking at particles that had charge. And so this particle must be something that has no charge. And so he comes up with the idea of this uncharged particle. Later, physicists began calling this particle a neutron. Very shortly after Chadwick comes up with the idea of a neutron, then physicists start the ability to measure said particles and find out that they weigh a little tiny bit more than a proton. Now, mistakenly, they began to think that the neutron was like a proton and electron put together. It's really much more complicated than that, as we talked about the nuclear fusion inside the sun. But that was the original mistaken idea. And so based on that, just a couple years after, just very few years after Chadwick proposes that neutrons exist, then Bode and Zwicky suggest that if a really massive star, if the core reaches a certain point, it could squeeze everything down, in which you're squeezing electrons into protons and making neutrons. And so they introduced the idea of a neutron star as this. Now, what would a neutron star be like? Well, if you imagine the sun and you have 1 solar mass and you squeeze the entire sun down to about the size of what a neutron star would be, basically squeezing all the electrons, the protons, everything down into one giant atomic nucleus. So a solar mass nucleus would be something around the size of the city of Fort Worth or Arlington or something like that. And so that would be about the size of a neutron star. So everything squeezes down to just neutrons. And so that was the idea, but that was just a concept. And problem is, this thing would be tiny. They questioned what it would even look like, because it wouldn't have atoms to give you the normal sort of spectral lines or black body radiation. And so what would such a thing look like? Being tiny, it'd be very dim. Even if it's very hot, it'd be very dim. And so there was for a while very little idea as to what this thing might actually look like. So the idea that Bode and Zwicky came up with is you have a big star, the core of the star collapses to this neutron star if it exceeds 1.4 solar masses. The resulting release of energy blows away the rest of the star, and what you have left is a neutron star surrounded by an expanding cloud of gas. Now, a number of decades passed, and then an Italian astronomer, Franco Cassini, comes along, and Cassini starts suggesting that a neutron star is not all neutrons. Mathematically, he said there should be some protons left in there. And now we know that if something is rotating and shrinks smaller, it rotates faster and faster and faster. So he suggested mathematically that a neutron star ought to rotate in like a second or so. And so instead of taking weeks to rotate like a star would, it'd rotate in seconds. And going around really fast with charged particles, which you still have a few protons left in there, maybe even a few electrons that didn't quite get all made into neutrons. And so what would happen is you would have this enormous amount of charge going around really fast that would create an enormous magnetic field. The magnetic field would have a north and a south pole. And he reasoned that Earth's magnetic field with the north and south pole traps charged particles in it, which then impinge on the Earth's atmosphere near the magnetic north and south poles. That gives you the aurora. So he thought something like that running into the neutron star would actually produce beams of radiation coming out. And so you would have charged particles trapped in the magnetic field that run into the north and south poles and produce these beams of radiation coming out. And now, the Earth's north and south magnetic pole don't line up precisely with the geographic north and south pole of the Earth. So in general, almost all magnetic poles are tilted a little bit from the geographic poles. Now, he then reasoned that as that happens, as the star rotates, then this beam would swing around in the sky. So sometimes if you're up here looking down, you would see the beam, but if you're in that same orientation here looking down, it would miss you. And so this beam would swing by pointing at you now and then. And so if that happened, you would see a flash of radiation coming out of the beam. In fact, he reasoned this would be such a powerful beam because you would also have so much magnetic energy that we know that E equals mc squared. With enough energy, you can make mass. You'd be making electrons and positrons, and they'd be running into the poles, flashing radiation out. And so some of these particles go flashing out too. And so you'd have this blast of radiation now. Now, interesting thing, 1968, there was a graduate student by the name of Jocelyn Bell, and she was working for a astrophysicist by the name of Anthony Hewish, and that was her professor. And her PhD research project was going to be using a radio telescope to look at what is technically called the scintillation of radio by the interstellar medium. The idea being, if you go up and look at a star with your naked eye, it tends to twinkle. That twinkling is technically in the technical terminology called scintillation, and that would be the stars that are flashing on and off and dancing around a little bit due to the atmospheric turbulence. So she was reasoning that radio waves passing through light years worth of interstellar medium would do a similar sort of thing. They'd be flickering a little bit. Now, no one ever measured that because normally radio telescopes are picking up very dim signals, and so you just point them and leave them on and collect the radio energy from that particular region of space and then add it all together, what we call integration. And so no one had ever tried measuring short-term variations of it. So she was trying to do that with the radio telescope to measure it, and what she discovered was, yeah, there's this scintillation in interstellar medium, but in several spots in space, she found little peaks that were evenly spaced in time. So it was like a little blast of static, psst, 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 coming in time and on a regular basis. And so just pulses of radiation. So she referred to them as pulsars and was trying to figure out what pulsars were. Now, what happened was her professor had read Cassini's very, very technical paper. It was very mathematical. Not a lot of people had read the thing, but Hewish had read it, and he realized that what his graduate student had discovered was the flashes of radiation coming from rotating neutron star. And so he analyzed her findings and announced that she had in fact discovered rotating neutron stars, because he put all the pieces together, what she discovered plus what Cassini had calculated. Now, interestingly enough, there's always conspiracy theorists that have to talk about everything. And so the conspiracy theorists immediately came out and said, aha, these flashing radiation things are actually navigation beacons, like lighthouses for flying saucers. Generally, the astronomical community discounted that idea. So now we have this huge discovery. We have the discovery of neutrons, the idea that they can be squeezed into neutron stars, mathematical analysis of neutron stars, and then a graduate student who discovers the neutron stars. So this is a big deal. We got to win a Nobel Prize for it somewhere. Who gets the Nobel Prize? Well, it turns out the discovery of it was considered the big deal, rather than theoretical analysis that led to it. So that let Body, Zwicky, and Cassini out. Chadwick had already been acknowledged for actually the discovery of neutrons, but though he did not actually come with the idea of neutron stars. So it turns out that Anthony PHYS wins the Nobel Prize. Generally, Nobel Prizes don't go to graduate students. There's several big discoveries that have been made by graduate students who their professor got the Nobel Prize. And so that's generally how it works. So, but everybody knew that Jocelyn Bell had actually done the work. So she actually became very famous for the discovery and for helping her professor get the Nobel Prize. So next thing we're going to talk about, though, is the actual properties of neutron stars themselves.